Alright folks, in this video we're going to be talking about four different types of colligative properties. So starting out with the first one, which is called the lowering in the vapor pressure. So anytime you have a non-volatile solute in a given solvent, the vapor pressure of that particular solvent will decrease as soon as it makes the solution with whenever you add a non-volatile solute. So now your non-volatile solute could very well be a solid, or it could also very well be a liquid. I mean, we can talk about like NaCl or KCl. Most of the salts are going to be non-volatile, or almost all of the salts going to be non-volatile, but not all solids going to be non-volatile. I can talk about dry ice. Dry ice is a solid, but it is not non-volatile. It could sublimate into the gas phase. So solids do have the vapor pressures, but most of them don't have the vapor pressures. As far as the liquids go, most of the liquids has vapor pressures, but obviously not all of them. And we can talk about glycols. Glycol is almost going to have zero vapor pressure because it's very dense and it doesn't really evaporate. So how much a liquid can evaporate and how quickly a liquid can evaporate translates to how much vapor pressure you're going to have. So suppose I have just water here in this cup. So when I'm looking at the water, I know this water is going to be making this hydrogen bonds right there. And in order for this, suppose this top molecule, top water molecule to escape into the liquid, into the gas form, you must break that interactions, all right? And that's why if you have those stronger interactions, it's going to be low vapor pressure because it's hard to break those, and you have low molecules escaping from the liquid phase onto the gas phase. However, as soon as you add NaCl, what really happens in the solution? When I'm just taking an example of NaCl as a solid solute, and you could obviously have other types of solutes. As long as it's a non-volatile, more or less it kind of stays the same. If you have NaCl added in there, I know that NaCl is going to get broken into Na plus and Cl minus in the solution. And suppose I go ahead and put this NaCl right, Na plus right in the middle of these two water molecules. So I'm still focusing on this water to kind of escape into the gas phase. But now all of a sudden, before it was making these hydrogen bonds, in addition to making those hydrogen bonds, it will also make extra type of interactions are called an ion dipole interactions. And you're not going to be seeing ion dipole interactions to be the new types of intermolecular forces made all the time. It depends on the types of solute. You may have very well a just in a solid solute that just dissolve in water but does not break into the ions. But in that case, you would still have some extra intermolecular forces made in there. So anytime you got these extra intermolecular forces made, now this water molecule will be held on more into the liquid phase, and as a result it's going to be hard for this water molecule to escape. So it's going to be hard for him to escape, and as a result your vapor pressure will decrease. And remember, if your vapor pressure decreases, you will have to heat up longer or heat up to a higher temperature to get to that particular boiling point, and in that case your boiling point will go up. But we'll talk about that in a minute, but let's just focus on the vapor pressure. So overall, what happens anytime you add a non-volatile solute, you will have these extra intermolecular forces made, and when you have these extra intermolecular forces made, it's going to be hard for it's going to be hard for the molecules to escape, and that results in the lower in the vapor pressure. So when we talk about what type of extra intermolecular force is going to be made, well, that could be just another ion dipole, or you could have just another set of hydrogen bonds in there, or you can just have another set of dipole in there. So it's just a matter of what type of solvent and what type of solute you're really dealing with. And it's important to be able to identify what are the new sets of intermolecular forces you're making in there. So how you really measure it, like how much the vapor pressure will go down when you add a solute. So there isn't a simple formula that you can always use. So it's going to be the vapor pressure of your solution is going to be equal to the pure vapor pressure times the mole fraction of your solvent. Okay, so this X looking figure is just called the mole fraction. The vapor pressure of the pure solvent is always going to be measured by this zero as in a subscript there, as in a superscript there rather. And then this P is just going to be the new vapor pressure of the solution. So make sure you have this formula down. Typically, what would you be given in a given question? You will have this pure vapor pressure given, and as far as the mole fraction go, you would have to figure out what the mole fraction going to be. And I could probably just rewrite that because it just doesn't look good. So you will have to find the mole fraction of your solvent. And once you have those two things, you can easily figure out what the vapor pressure of a resulting solution going to be. Now, that was just for the solute that's non-volatile, but what if you deal with a solute that's actually volatile? And that would happen typically when you have two liquids being mixed up. And I can talk about, alcohol mixing with water. And in those cases, one of them will be the solute and the other one will be the solvent. And the easier way to figure out what's the solute and what's the solvent, your solute is going to be the less in amount and your solvent is going to be more in amount. And since both of those are liquid, they're both going to have their own vapor pressures. And when they have both of them has their own vapor pressures, your resulting vapor pressure is going to be the sum of those two. Okay, and let me take a generic example of liquid A and liquid B. Suppose I have two liquids in there. So when you have, and I can maybe talk about liquid A being less in amount, so that would be my solute, and liquid B being more in amount, so that's going to be your solvent, so just hypothetically. So I know liquid A is making some sort of interactions with the liquid A, so those are your solute interactions. And then I can also talk about B is making interactions with B. So those are your solvent interactions. So that's your solute interactions. And those are your solvent interactions. Now, when you do mix A and B, in addition to those AA and BB interactions, now you're going to be making those AB interactions as well. So those are going to be your solute solvent interactions. Now, dealing with a volatile solute is going to be a little bit difficult because you got multiple interactions to deal with now. And if you do make an ideal solution, so it's just like an ideal gas is, it may not exist in real life, but you assume that if you do make an ideal solution where the magnitude of these solute-solvent interactions is equal to the magnitude of solute-solute and solvent-solvent interactions. So another way of saying all these interactions, the AA and the BB and the AB are going to be roughly equal to one another. And if that's the case, suppose I have this green one here to be the mole fraction of B, and the A is the this orange one is the mole fraction of A. So when you have only B, so the mole fraction being 1 right there, so suppose you have a vapor pressure at this particular time here, and then when there is no B, then your vapor pressure with respect to B is going to be 0. So you will have one straight line that would look like this. But then at the same time, you could have for the A, if you have only A, that means the mole fraction of A is going to be 1. So suppose I'm right there in that particular case, the vapor pressure. So I'm just hypothetically picking up those values on the y-axis for the vapor pressure. But if your mole fraction of the A is going to be 0, then you're going to be the vapor pressure with respect to A is going to be 0. So that's going to be down here. So I can go ahead and draw a straight line here. So that's how it's going to look like. Now, if I pick any given point, these are going to be the vapor pressures of your two liquids at a given time. So I can, if I want to get, if I have to calculate those, I can do the vapor pressure of A is going to be the pure vapor pressure of A times the mole fraction of A. And then I can do the same thing for the B. The vapor pressure of B is going to be equal to the vapor pressure of pure solvent B times the mole fraction of B. So those are the vapor pressures. The PA and the PB are the vapor pressures once the solution has been made. So if I go ahead and pick a point there, so suppose I pick the point right there. So at 0.4 mole fraction with respect to the B, and that's going to be 0.6 mole fraction with respect to the A. And if I pick those 2 points, I know what my vapor pressure is going to be for the PA and the PB. So this is going to be your PB right there, and this is going to be your PA right there. So then what would be the total vapor pressure at that particular time? So your P total is going to be equal to the vapor pressure coming from A plus the vapor pressure coming from B. So all those three different formulas right there, they're going to be extremely important when you're looking at liquids being mixed up together. So when we go back into this chart here, and I can go ahead and draw out a line that meets the maximum vapor pressure. So another way of saying this point right there is going to be the P total, and that's going to be equal to the PA plus the PB. Now this holds true when the solutions are ideal. So what that means, your solute-solute interactions, your solvent-solvent interactions, and your solute-solvent interactions are equal to one another in terms of magnitude. Okay, but what happens when they're not equal? And that's usually going to be the case for the most part. Your formulas doesn't really change, like the PA, PB, and P total, how you calculate that doesn't really change, but it's just the deviation from the Raoults law, like how that's going to work out. So let me give you a couple of scenarios here. So I'm going to do here, just copy this graph down onto right here. So I'll take out a part of it. I'm going to take out this momentarily. And ideally, this is how it should look like. So I'm going to make dash lines there. So that's with respect to the ideal solution. But then there is a good chance that your AB interactions, because we're mixing up those two liquids there. So the solute-solvent interactions are actually greater than those AA interactions and BB interactions. So what that means, they're going to be held on together with a stronger forces, and in that case, their vapor pressure is not going to be as you would see in an ideal solution, but you would have something like this. You would have a negative deviation there, and I can say the same thing where for the A, it's going to have a negative deviation there. And then as far as the total go, it's going to be the same. You will have a negative deviation. So that's going to be your real vapor pressure in that particular case. So that's called the negative deviation from Raoults law. And that would happen when you have stronger intermolecular forces between the solute and the solvent than the individual interactions between the solute-solute and the solvent-solvent. So in that case, your solute and solvents are held on together with a stronger forces, and it's going to be hard for the solute and the solvent to escape, and that will decrease the overall vapor pressure. Now I can say the otherwise as well. So when we say the otherwise, so let me get another scenario there. So kind of running out of space there, but I'll make it smaller a little bit. So let me go ahead and take out some of that. So the other scenario would be, what if your A-B interactions are actually less than your AA and BB interactions. So another way of saying your solute-solvent interactions are actually going to be less than your individual interactions between the solutes and between the solvents. So in that case, your A and B will be repelling one another. You can kind of think of that way. They're going to be pushing each other out, and as a result, they would be having a higher vapor pressure than expected. So if they have a higher vapor pressure than expected, you call that a positive deviation from the Raoults law. So it's going to be, let me change the colors there, so it's going to look like this. So you'll have one of them looking like this. The other one would be looking like this. And your total would be going up, so where you're going to have the positive deviation. So this is going to be positive deviation from Raoults law. So this would happen when you mixing the two liquids that has different types of interactions. So I can say, the solute is polar and your solvent is nonpolar, and you try to mix those up and they don't really like one another, so they're going to be start pushing one another out. And you have to make sure they are miscible. Sometimes if they're not miscible, then they will make two different layers. But the bottom line is their interactions are going to be not as strong between the solute-solvent compared to the interactions between the solute-solute and between the solvent-solvent. So in that case, you get a positive deviation from the Raoults law. As far as calculation go, your formula is still going to be the same. You're still going to be have to figure out what's going to be the vapor pressure of your one liquid using this formula and the second liquid using this formula, and then the total vapor pressure is going to be the sum of those two vapor pressures you get. As far as the deviations go, these are going to be more or less like conceptual based questions. You don't know like how much it's going to deviate, but they would ask you like if you have a negative deviation, then how would the interactions going to be behaving, and otherwise as well. Let's talk about freezing point depression and boiling point elevation. So those are your second and third colligative properties. So I have both of those written down together because their formula is kind of very similar to one another. You may have wondered why you really add salt on the icy roads. That's because that will lower the freezing point of the water, and in that case, it may stay in the water form rather than in the ice form, and that helps. As long as your temperature of the environment is kind of somewhere around 0 degrees Celsius or maybe like 32 degrees Fahrenheit. If it's like too low, then it may not help in that case. If your temperature is too low, we're looking at like negative 18 degrees Celsius or maybe somewhere around 10 degrees Fahrenheit, then adding the salt, it's not going to be the solution. In that case, you may have to take out the ice. And then the opposite is true when it comes to the boiling point. So the boiling point actually increases. So remember, your vapor pressure decreases when you add a solute, but then as far as your boiling point go, it's going to increase because you would have to make your vapor pressure equal to the atmospheric pressure before you get to the boiling point. And to make the vapor pressure equal to the atmospheric pressure, you would have to heat it up at a higher temperature. So the equations are going to be very similar. For the freezing point, let's say for the freezing point, you would have the delta T equals I m Kf. So your delta T is going to be the change in temperature. Your I is obviously going to be the Van Hoff factor. Your lowercase m is the molality. All right. So keep in mind what concentration terms you're going to be using for those colligative properties. Your Kf is going to be the freezing point depression constant. And for water, you don't really have to memorize those. For water, this Kf is going to be 1.86 degrees Celsius over molo, which is the same as molality. Um, any other solvents that you're going to be given, or even the water, if you're given in the question, you will be provided the freezing point depression constant. You're not expected to memorize those. I do want to mention, like, how do you really use this delta T? So when, suppose you know the I, suppose you know the Kf, and you figured out what the molality is, and you calculated the delta T. Suppose the delta T came out to be 2. All right, so that's your change in temperature. So logically, remember your boiling
Freezing
point has
point.
to go down by that much. So if you're talking about water, so if your water is the solvent in that case, what's going to be the normal freezing point for the water? Well, water, I know if freezing, it freezes at 0 degrees Celsius. But as soon as you find this delta T to be 2, that means your new freezing point is going to be 2 units below the given freezing point. So it's going to be minus 2 degrees Celsius in that case. If you have another solvent, suppose get a random solvent that has the freezing point of 10 degrees Celsius, all right, so then what's going to be your new freezing point in that case? Your new freezing point in that case is going to be 2 units below because your delta T came out to be 2, so it's going to be 8 degrees Celsius. So you want to think of that as logically as well. You may see some books using the values of Kf to be negative just to kind of take care of that problem, but it's better to think logically. Your freezing point always going to go down by some temperature, by some units from your normal freezing point of the solvent. So, and the opposite is going to be true for your boiling point. So let me go ahead and write down the boiling point equation first. It's going to be similar. It's going to be delta T Im, but instead of Kf, now you're going to have a Kb. So Kb is going to be the boiling point elevation constant. Everything else stays the same. You're still going to have the change in temperature, you're still going to have the molality, and you still have this Van Hoff factor. Okay? Now, what happens when you do calculate the delta T? So suppose the delta T came out to be 2, and you're using the water as your solvent. So what's the normal boiling point of water? That's something you are expected to know. What's the freezing point of the water and what's the boiling point of the water? If you're provided any other solvent, they would give you the freezing point and the boiling point depending on the type of question asked. So the boiling point is 100 degrees Celsius, but then what's going to be the new boiling point in that case? Well, remember, the boiling point elevates when you add the solute, so as a result, your new boiling point has to go up 2 units from your original boiling point, which was 100, so it's going to be 102 degrees Celsius. So that's something you want to keep in mind under in which particular case you're going to be going down and which particular case you're going to be going up. So that's why we have these names like depression means it goes down, and we got this elevation means it goes up. All right, so those are your other two colligative properties. And then as far as the calculation questions go, you will be asked, like you could be asked the delta T, or you could be asked the new boiling point or new freezing point, and will be provided enough information to find out the value of Van Hoff factor, the molality, and the Kf or the Kb will be given to you as constants. Okay, let's talk about, oh, also the Kb for water, just if you guys wondered, it's going to be 0.512 degrees Celsius over the molality. The last colligative property we got is called the osmotic pressure. So the simple definition of osmotic pressure is going to be the pressure required to stop the osmosis. All right, so let me give you an example, like how does the osmosis really work? The osmosis is going to be the flow of solvent, typically water because that's what we really deal with for the most part, but obviously not necessarily limited only to the water. Then it flows from the low salt concentration to the side that has a high salt concentration. Okay, let me give you an example. So suppose I have this container here and I got the water, and the water is same on both sides originally, but then all of a sudden I add some salt on one side, and I can maybe talk about adding some NaCl on to this left side. So now you have high salt concentration on this side, and then you just have pure water on the other side. And then those two compartments are going to be separated by so-called a semi-permeable membrane. So semi-permeable membrane, it allows only selective molecules to flow through. And for the most part, the semi-permeable membrane is just going to be typically allowing the solvent. Your cell membranes inside the human bodies or inside the animal bodies, the cell membranes are semi-permeable where it allows only the water molecules to kind of pass in and out easily, not any other ions. Yes, the potassium and sodium does pass through the cell membranes, but that's those through the channels, not just through the diffusion not through the diffusion. But water can be passed through those semi-permeable membrane or those cell membranes. Now, since you have high salt concentration on the left side, the net flow of the water is going to be going from the right compartment to the left compartment like this. Your water always going to flow from low salt concentration to the side that has the high salt concentration until the salt concentrations on both sides is roughly equal to one another. So now what happens when you have this water flowing from this right side to the left side? We're going to have this water from the right on the right side, the water level is going to go down, and on the left side, your water level is going to go up. So that's what I'm going to make now. So I'll take some of this out here. So let's say it went down that much, but then on the right side, on the left side, you will have that much water kind of going up. So then there is going to be a height difference in the water. So whatever the height difference is going to be, that's going to be the measuring of osmotic pressure. So this right there is going to be the osmotic pressure. So another way of saying, if you can apply enough pressure to stop the flow of water into the left compartment, that's also going to be your osmotic pressure. And if you have to measure the osmotic pressure, you measure what the height going to be using a ruler, and then you can say that in terms of either millimeters of mercury or either centimeters of mercury or even meters of mercury, depending on how high it goes. Okay, so now how you really calculate it? Suppose you're not really doing experimentations, but just theoretically, how would you calculate the osmotic pressure? Your osmotic pressure has a symbol that kind of looks pi, but it's not really pi. It's just called an osmotic pressure. It's going to be equal to I uppercase M RT. All right, so this is the equation going to be for the osmotic pressure, and make sure you're aware of it and you're aware of it what those terms mean. So we got the osmotic pressure, and I again going to be the Van Hoff factor. Your R is going to be the gas constant. So what's going to be the value for the gas constant? Since we're measuring the pressure, it's going to be 0.0821 atmosphere liters divided by moles Kelvin. And then uppercase M is going to be the molarity. Okay, so now keep in mind we use molarity here, not the molality. So for the freezing point depression and the boiling point elevation, we used the molality. For the vapor pressure, we used the mole fraction. And for the osmotic pressure, we're going to be using the molarity. And then the temperature is going to be always going to be in the Kelvin scale, and that's going to be the T in that equation. So if you know those um, four values there, you can easily figure out what the pressure is going to be. And if you have to do it experimentally, you can do so if you have this experimental setup where you measure the height and the difference, and now you have the you have the osmotic pressure in that particular case. Now, where is osmotic pressure really used, or where is this technique, like semi-permeable membrane and all that, really used in real life? Let's take an example. So suppose I have this RBC, so this is going to be your RBC that I have drawn in there, or red blood cells, or even just the cell inside the body. It doesn't necessarily have to be only RBCs, it applies to other cells inside the body as well. So when we drink water, so this is going to be the drinking water. So when we drink the water, the concentration inside the RBCs or inside the cell for the salt is going to be the same as outside or in the drinking water. So as a result, there is no net flow. So I can say the concentration, or the salt concentration inside is equal to the salt concentration outside. So since that's going to be equal, there is not going to be any net flow of the liquid. Well, I'll repeat that. There is not going to be any net flow, but that does not mean there is not going to be any flow of the water. You may have some water going inside the RBC, but then at the same time, you may have some of the water from inside the RBC or inside the cell coming out into the solution. So as a result, there is no net flow of the water. And that particular solution is going to be called an isotonic solution because it has the same concentration inside the cell and surrounding the cells. But now, suppose all of a sudden you start drinking ocean water. So what happens when you drink ocean water? Well, ocean water has high salt concentration than what you really need. So it's not really recommended to drink the ocean water. So when we do drink ocean water, so let's see what's going to happen to this RBC. So I can probably just duplicate that. So now you're going to have low salt concentration inside the cell and high salt concentration outside the cell. So I'm going to go and write down here high salt concentration. So since you have a high salt concentration, which way the water gonna flow? Well, remember your water always flow from the side that has low salt concentration to the side that has high salt concentration. So you will have water coming out of the cell like this. And then when water comes out of the cell, what's going to happen to the cell? They're going to get smaller. So another way of saying it, as a result, eventually what's going to happen to that cell, if I just make that down, it's going to get smaller and smaller. So that's how it's going to look like at the end of the day. So it gets shriveled or it gets smaller. So smaller RBCs or cells will result in that case. Now, this particular solution, when you place this RBC or the cell that in the surrounding solutions, and when you have high salt concentration, that one is going to be called a hypertonic solution. That means you got higher salt concentration than what you have inside the cell. Now, the opposite can be true as well. What if you start drinking so-called deionized water or DI water? And you may see this also called to be distilled water. It just means there's no ions in there at all. So in regular drinking water, you still have some ions and minerals in there, and that's what makes it isotonic with respect to the salt concentration inside the cells. But when you're drinking DI water, there's no ions whatsoever. So as a result, that's going to be your hypotonic solution with respect to the RBCs. So what happens when you have the RBC in that case? So let's suppose the RBC in there. So which way the water is going to flow? So now you have low salt concentration outside or in the surrounding of the cells. So since you have a low salt concentration, the water is going to move into the cell because remember your water always moves from low salt concentration to the high salt concentration. So since your water is going to move into the cell, what's going to happen to this RBC or this cell? Well, clearly it's going to get bigger. So I can go ahead and write that down here. So it's going to get bigger or it will be swollen. And you can have this cell to be burst if it gets bigger. So that's how the net flow of the water is going to take place when you drink either the ocean water or the DI water based on the need basically. And obviously the faucet water is isotonic with respect to the concentrations that we have inside the RBCs. So those are going to be your colligative properties. In different sessions, I'm going to be talking about how to use some of those equations to solve the problems. If you have any questions, feel free to leave any comments in the section below.